Okay, let's do the traditional proof for why 2 to the power of n is equal to the total number of subsets a set with n elements has. So we're going to be asking, is the following statement true? That a set A, defined as this, has 2 to the power of n subsets for n greater than or equal to 0 number of elements. So this means that the set has at least 0 or more elements in it. So this is going to be a proof by induction, and the reason I know this is because oftentimes proofs by induction are what you have to do when you have an inequality type of condition you have to meet. So how do we start this proof? Well, first, because this is a for all sets, right? This is just a general set. We start with a let. We let A be a set such that A is equal to x1 xn, where n is greater than or equal to 0. Now, I don't know if this is the correct notation for the subset, because I'm not sure how you would write the empty set in this case, but it should be fine. So let's go ahead and try and prove the base case. What is the base case going to be? Well, the base case is going to be when n is equal to 0, or in other words, when the set is empty. So we say, let A equal the empty set. Then we have 2 to the power of 0 is going to equal 1. So there is in fact, or no, let's have a bet. No, that's not correct. We say then the empty set has only one subset, which is itself. So the number of subsets when n is equal to 0 is going to be 1, which is going to equal to 2 to the power of 0. So it's looking like this statement is true for our base case, that an empty set really does have only one subset, which is going to be itself, which is the same as saying 2 to the power of 0. Fantastic. Then we want to do our induction step. So let's go ahead and write that down. So for our induction step, we need to suppose that for some set S equal to, let's use A1 AN, that the total number of subsets is 2 to the power of n. Now, why can we suppose this? The kind of reasoning in an induction step is, because we showed this is sort of true for the base case, we can kind of suppose it's going to be true. But what we want to prove is then want to prove that if the set S is going to equal to A1 AN and AN plus 1. So we want to prove that it's going to be true if we add an extra element to A, or to our set. We want to prove that if then there are 2 to the power of n plus 1 subsets. Okay, so this is the hard part. Where do we go from here? Well, from here what we should notice is the set S, we can split it up into having two categories of subsets. It can have the subsets containing only the elements A1 to AN, in which case we just get our induction hypothesis and say that's equal to 2 to the power of n. And then we can say, well, if you have a subset that includes AN plus 1, all of the possible subsets, including AN plus 1, is just going to be 2 to the power of n as well. So what do I mean by this? So we can say that S can have subsets, including elements from A1 all the way up until AN, which have 2 to the power of n subsets from our induction hypothesis, then S can also have subsets with the element an plus 1. And before I write my next point, let me just quickly better explain what I mean here. So we've already seen that if we're just looking at the number of subsets that have just the first n elements, we know there's going to be 2 to the power of n possible subsets. But then if we look at all of the subsets that have an plus 1, if we look at the remainder, we're basically asking if you have an plus 1 as a fixed element, how many possible elements or how many possible subsets can you make when this is fixed? And we know from our n choose k notation that's going to be however many elements we have, it's going to be n choose 0 plus n choose 1 all the way up until n choose n, right? So, and this down here, because there's this many possible ways we can add something to a set that has to include the element an plus 1, this is just going to be adding 2 to the power of n, or these possible elements to create another subset. So we know that then S can also have subsets with the element an plus 1 where there are 2 to the power of n possible subsets with an plus 1. Then we can say, therefore, there are 2 to the power of n plus 2 to the power of n possible total subsets for S is equal to A1, comma, dot, 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 AN, comma, AN plus 1. Let me make sure that makes sense. And then we can say, so 2 to the power of n plus 2 to the power of n is going to equal to, oh, I misspoke up here. We want to show, oh no, I did everything right, I'm just getting lost. Yeah, we want to show that. So which is going to equal to something plus something, something plus the same thing, something plus itself is the same as saying 2 times itself, right? If we have 3 plus 3, that's the same as 2 times 3. If we have x plus x, it's going to be 2x. It's just going to be 2 times itself. So that's going to be 2 times itself, which is going to equal to 2 to the power of n plus 1. So there we go. We have shown that an element or a set, if you add an extra element to it, the total number of subsets is just going to be 2 to the power of n plus 1. So there we go. You can now write out your conclusion if you would like to. I'm personally not going to, because that's just an extra detail here. But we've shown the base case is true, that when you have 0 elements in a set, that the total number of subsets is going to be 2 to the power of 0. And we've shown that if you simply keep adding an element to a set, the total number of subsets is going to be 2 to the power of n plus 1, or 2 to the power of the previous number of subsets you have, or sorry, number of elements you had, plus the extra 1 every single time. So we've shown that this statement is in fact true.